Hello, Connor Bush again, back with homework 2. This is part B. So I'll read part B and then get into it. So part B, with the liquid height, temperature, and concentration of A calculated in part A as initial conditions, calculate the response of the system if the flow rates change from 0.55, 0.28, and zero point 0.6 cubic meters per second, respectively. So we're going to jump back into the code that I had earlier, and then ultimately we're going to plot this. So from plotly dot subplots work make subplots. Do all of this. We're going to need some time aspect eventually. So and we're going to set that to 100 seconds. So now we have new conditions for the flow rate. So we're going to call this vector or array Qn2. And then we're just going to paste in these values that we had earlier. And then we're going to do a little quick copy function by doing this. So we can copy the arrays we had above, and we can differentiate the two if we need to. So now we're going to have to do something similar up here, except for we're going to use solve IVP. We're going to call the lambda function again, however, this time for t and v. So the right-hand side, we're going to look at t, v. That is our use of the lambda function. Our new values Qn2, Ca in 2, and then T in 2. Our time span is going to be from 0 to T end. Our Y naught is going to be our V naught that we had saved from our initial parameters that we got from part A at steady state, which is what the instructions are asking for. And then method, we're going to use Radu, and then we're going to make sure that the dense output is true. So we can use this, the solutions integrated. So now in terms of plotting, make a set of points from 0 to t end, 500 points in between. Our H plot, CA plot, these are all going to be on the y-axis, and then T, capital T equals, we're going to use the solution from sol2, the variable, and then we're going to use T plot as the time parameter. So now we can get into the actual plotting of these. So if they type, so we're going to have just one row with 3 columns. I'm going to add our first scatter in the first row, first column. Our x-axis is going to be the time, and then our y is going to be the height. And then we're going to name this tank level in meters. And then I'm just going to copy this because we're essentially doing this 3 times over, changing the column. And then our y-axis, this is not the tank level, this is the concentration of A in moles per cubic meter. And then once again, for our temperature, we're going to name that temperature in degrees Celsius. And then I'm going to update the layout. don't think it's template. Yeah, it is. Great. So this is, or all three of our plots. So this one in the first column is the tank level as it approaches this next steady state from changing the flow rates. And then this is the concentration of species A as it reaches the next steady state. So you can see it approaches around 0.4 moles per cubic meter. And then finally, our temperature as it reaches steady state, the next steady state at around 81.2 degrees Celsius. So that is part B for homework 2.